Good morning, everyone. Welcome to the third day of ZuriHac. The weather has taken a bit of a downturn now. Jasper said there's not enough coding happening, and he said we have to change the weather, and so I said, okay, and I changed it. And so I guess people are doing their stuff now. Just before Alejandro's talk, I'd just like to mention some things. Lunch today will be in the Mensa that's just directly downstairs. So it's going to be open from around 11 o'clock to 1:15. So try to be there between 11 and 1, and try not to be all there at the same time. But I guess that's fine. We have other things happening to space that out. So that's good. There's also a vegetarian vegan option, just for your information. Yeah, and so there's a menu. You pay with cash or card, and that should be fine. Yeah, so that's lunch today. So we also have quite a lot of food remaining from what you gave us for the barbecues. So please go to the fridge in building 1 on top next to the coffee machine and just collect the food that you have there. And I guess, should we just open it for everyone? Anyone can just take anything what they want? Yeah, if you see a sausage you like, please help yourself. Then, so there will be a third session of the beginner's track just after Alejandro's talk. Just give me 10 minutes and then we'll start there again with the beginner's track again. So beginner's session for the beginner's track. Yeah, and also we'd like to thank you very much for helping out at the end of the day. It worked really well. Thank you very much, everyone. Cool. So, Jasper?
Yeah, and then one more thing. So at the end of today, we'll have project presentations. So if you worked on something during ZuriHac, it's very unlikely, I know, you will have like 15 minutes, or you can do like 5 minutes to just kind of like show it to everyone. So I think that starts at 3, but I'm not super sure, so check the schedule. And then now we're going to continue with Alejandro, who's going to turn sort of like the DSL we built in the last session into a real program.
Hopefully. Yeah. So just to be clear, the goal of today is because I think this weather chain happened because somebody in the beginner's track said like, oh, this is too difficult, fuck it. And I'm going to use JavaScript for the rest of my life. I think we somehow, enraged the gods of weather. So now we are going to sacrifice a few binds in our monadic altar to try to make it happy. So if it works, that means that I will be able to visit Rapperswil without rain. Otherwise, well, it's your fault. So, you've been the other day in the other part, we talk about like domain-specific languages, and essentially everything we did was kind of pure programming, a lot of ASTs and functions. But if you try to build an application, of course, you always have the terrible, most boring parts below. You have to serialize the stuff, communicate over networks, and there are errors because files sometimes don't exist, servers are down, and then you want to be fast and you want to do concurrency. So, my whole idea with this workshop is we will build this interactive game and then we will communicate. We will have people playing at the same time this Pokemon card game. It was awesome, except that I realized that that's like maybe too much for 1 hour and a half. So we are going to change to an even cooler game, throwing dice, and just see who gets the biggest result, which is awesome. Look at the guy. I mean, it's this like super cool guy throwing dice, like a lot of dice. And to make it even better, it's going to be dice roll in the cloud. So why we need a server, it doesn't matter, but that's like what we sort of can do, right, in 1 hour and a half. So that's what we are going to do. We're going to have some server, and then people will connect, throw dice, and then the server will say, okay, of all of you, I have randomly chosen these numbers for your die throws, you win. That's enough. So hopefully the code to, like, the logic is going to be like 3 lines, and all of this will be exposed in how you communicate, how you do a server, and the kind of things I want to show you today here. So more or less, the stack we are going to use is Haskell, of course, as the implementation language. Then a library called Network Simple, which is like for networking, and it's simple. Sounds reasonable. And then I'm going to introduce a few libraries for serialization, namely binary and ASON. And then I'll talk a bit at the end about how we can do concurrency and how you can communicate several threads running using this wonderful STM that stands for Software Transactional Memory Package, so which is, for me, like the gold standard of how you deal with shared data within Simon approves for how you deal with concurrent data in programs. So let's start with an even more simple game. That's a one-person dice roll, so it's going to be a server. The server is just waiting, and then you send a client request. Please, I want to die a roll of 20 faces, and you get back 17. That's what it's going to happen. You can implement this as in X case it is strip. You can actually use random. That's not important here. So in order to do this, we are going to use this network simple thing. And network simple is essentially based on two functions. One is this, and that's how you build a server. And especially if you are starting with Haskell, you might stare at this, see that there is no documentation below, and that's everything we have. And it's like you are supposed to make sense of what it is just because of the type. And the thing is that we can actually, with the type and the few comments, we can try together or guided by me to try to figure out how this serve is doing. So, if you have done a few socket programming anywhere else, essentially what the server does is it listens into a port, and then when a client comes, it decides, do I accept the connection or not? And then if you accept the connection, I think the method is literally called accept in the C library, then you get from the operating system a socket or a way in which you can communicate, right? And if you are doing this like in C, for example, you have some complicated handling because, okay, you are listening, but somebody comes and you have to accept that you don't want to accept in your thread because then you will be blocking the thread. You want to do it in a separate thread because, well, you want to keep listening for stuff. So you have like a loop of listening things. And then the other thing, which is like a spawning new threads for each client. You can essentially imagine that's how any TCP server works. The server is there listening, and every time there is a new client request, a new thread is spawned. And this is exactly what this is doing. But let's again, as I was saying, look at the signature. So we have a couple of arguments. So we have this monad IOM. I don't want to enter into that, but that's essentially saying that within this block, we will be able to use IO actions like print to the screen or send files over the network, things like this. And then there is the thick arrow, and then we have two arguments, the host preference and the service name. And if you read below, that's essentially that's how you tell where you are listening. So you usually say, oh, I want to listen to everybody in my network. So you use something like asterisk, a star, something like this, and then the service name is actually a bad name because it's actually the port. So you do the typical, I'm listening at port 8080. And then you have this thing, which is a function, and again, if you remember what I told you the other day, there is all this thing in which we are now, because we are in a function language, we are using functions for things which maybe we didn't thought about. Like the other day we were doing this to represent card actions. And here what we are going to do is that instead of having to handle all this spawning of a thread itself, we are going to give a function. And this serve thing will for every incoming connection, will automatically do the acceptance and run this function. And because this is a function, we can run it several times, one for each client, and do different things. So that's exactly what this third thing is doing. And you read below, it says computation to run in a different thread, so it sort of goes into that direction. But the point here was that if we are reading these kind of signatures, very often we find with regular arguments like the host and the service, and then we sometimes find functional types. That's usually something which tells you, oh, there is some sort of callback. Something is going to be called in my behalf, right? So in this case, what happens in each thread? Questions about this? Again, the goal for this was, like literally, if you are ever told, please use network simple, you will get this documentation, and I think it's very useful to practice, okay, how do I make sense of what the library is doing here? Yes? Oh yeah, the question is what it says with this function never returns. So this is actually part of the documentation, but so this serve function, it's like an infinite loop. So when you accept a connection, it listens again. So it never ends. So you can throw an exception or something like this to make it stop, but like the implementation itself never ends. It's always listening. You don't have like a escape hatch to say now please stop listening. You have to like literally Control-C or something like this. But that's just how the implementation works. You could imagine a more complicated thing which, like after each connection, you decide whether you keep listening or not by returning a Boolean or something like this. But just this is the simplest function of the network simple thing, so it just keeps going all the time. Good. So as I was saying, serve takes care of listening all the time on the given port, and then whenever a new connection comes, it accepts it, spawns a new thread. This part is going to be important later when we talk about concurrency, because that's where our concurrent clients are going to come from, right? Different threads which are spawned by serve, and then it runs the callback argument to do whatever you do for this client. So the second thing I wanted to show you is a pattern which is also very common when you do these kind of things, like when you are talking to a client, and then you are accepting requests, and then you essentially want to accept to get a request, and then do something, and then wait for more requests. And I call it the Go pattern because people always call these kind of functions Go, and the idea is that, well, you have a function Go, which does something and then just call itself with the same argument at the end. So it's like how we do the infinite loop, which again, maybe if we did it in C, we will have a while true. And here, that's how we do this Go thing. So essentially, what your server is going to do right now, how the skeleton looks is that we are going to call serve, we are going to listen to every incoming thing on port 8080, and then, remember, we have to give a function which is the callback. So the rest of the block is going to be the callback function, which in this case is going to perform some initialization. I'm not showing here, so imagine we have to initialize, I don't know, something on a table for each client, and then we go into the Go loop. So that's this Go function, which we, again, within the Go, we read and parse a request, we send the response, and then go again. So that's, again, how we do the looping. So I find this is quite common. I'm sure there is ways to maybe abstract this pattern somehow, but I also find that it's quite readable. So that's how I use myself and what I see other people using. So here is like all the code then we need. So now I'm just showing the Go function, which is like it's within the where. So this dice server doesn't need any initialization because that's just a general pattern, but in this case, dice server doesn't need this initialization. And the Go, essentially, as I said, is going to read a number and then create the, throw the dice, get the result, and send it back as a number. And this is done here. And again, I'm going to guide you a bit on what it's doing here. So there are two functions. The receive, that's here. And the send, those come from this network simple library. Those are the functions in which you say, please, I want to receive this number of bytes from the network. Please read the next, in this case, 8 bytes. Or I want to send those bytes to the network. And you get back a byte string, actually, so not show from all the string types Andrew talked about yesterday, the byte string, the one which actually represents bytes, not text or anything like this. So the receive and send are, I think, as easy as you can get. I mean, you have to say in which socket you want to send, where you want to send, and what you want to send as a response. And then two things may happen when you receive. It might be that you don't have anything else to be received because the client has closed the connection, or that you actually get your 8 bytes back. And that's what this case with nothing adjust is doing. If the case is closed, I'm done. Otherwise, I'll keep going. And I wanted to actually focus on this nothing thing, because that's also kind of part of this Go pattern that, the Go, I said we always go through the loop, but there is a way to stop at some point, which is not call myself again, which is essentially what is happening here. If I don't get any more bytes, then I'm done. I don't call myself again. So in this case, I return pure of nothing because, well, I don't really have nothing useful to return. And I'm done. And this will actually network simple mean that your callback is done, so the whole connection will be correctly released and the resources will get back to the operating system on all of that. All of that is taken care of you by this thing. And otherwise, you go over again. Good. So what? Yes? So how this works, that was the question. So this receive is actually using the operating system thing, which you block until you have 8 bytes on the socket. So this will block. So this is, again, a very simple thing. It's all blocking things. The same will happen with send. Like, it will block until the thing is sent, or maybe put into a buffer by the operating system. But it waits until the approval of the operating system. So that's why the code can be so simple, because you actually wait until you have your 8 bytes, and then you give it back. If the client, so the question was, when will the nothing branch come? And if the connection is closed, then the operating system has a special error code, which is, I don't have anything else. So it's not blocking because it knows what to tell you. It just returns like, one of these -4 thing is underlined, which means I don't have more bytes. And then this is transformed by the library to nothing. So cool. So what it's missing to understand all of this is actually how we get this byte string, which again is just a bunch of bytes, in this case 8 bytes. But we want to make sense of those bytes as a number. So we need somehow to decode that string of bytes into an actual number. And to do this, we use this decode function and this. Well, the other way back is the encode function, and those come from the binary thing, from the binary serialization library. So that's like the missing part. Essentially, we get all the bytes. We need to make sense of them. Just because decoding integer it's hard because it has who knows how big it is and so on. I'm using here word 64, so the base library actually comes with a bunch of signed and unsigned numbers with different widths, so that's very useful in this kind of situations where you are actually talking to a network and you really want to have an 8-byte integer and not something else. So let's go a bit into this serialization business. So if you look at Hackett, so like the package repository, you will see that there is a lot of conversion libraries to and from byte string. I mean, there is, I said binary. There is also serial. I think, okay, the two are the same, except that one uses strict and the other lazy byte string, and I never remember which is the right one. Then there is Async, which is like the library to do JSON coding and decoding. And I don't know, if you have to talk to something like Kafka, it uses this thing called Abro, so there is a library for this. So, I mean, given that Haskellers like to write like parsers and decoders, I'm pretty sure there is something or 5 different ones for every possible format you can figure out. Actually, using these serial libraries, it's quite easy to write a deserialization thing, Haskell. But never mind, that's not the important thing. The important thing is that they all follow the same pattern. You always have a type class or 2 type classes. So some libraries like Async prefer to say, oh, there are something which I can convert to JSON and some things which I can read from JSON, and I want to separate these 2 worlds. Another, like serial, say, oh, if I can serialize, I can deserialize, and the other way around. So, I mean, think whatever you want. Most of the time, this is decided upon you by the library writer anyway. And then you always have this kind of encode, decode function, which require your data type to be serializable or convertible to the format or something like this, and then it turns this thing into the actual byte string, and then you have a decode which goes the other way around. So it's I would say it's kind of a quite usual, quite common example of type classes in Haskell, right? Like how you turn things into a format. Yes, question. Sorry again?
Did you say what the to format and from format?
Yes.
I maybe missed that.
Oh, so I'm assuming. So I said that. So the question is, what is this to and from format coming from? Yeah. Yeah. So I said there is like to JSON and from JSON. So in general, it's like gonna be like from any format and to any format. So I haven't defined those ideas that you will have to JSON, to Avro, to whatever. So. Yeah.
So, I can understand that you specify the format you're converting into or from, like JSON, something else, but I'm not quite sure why you need to say the to part and the from part as well.
Oh, why you need is to? So, yeah, right. Because in many cases, like. The library writer have defined these 2 different things, so 2 different type classes. One has encode and one has decode as 2 separate classes. Because I've never found this a scenario, but I guess they found that sometimes you only want to decode stuff, but don't encode it back, and then you want to keep this because you want less code. I'm the person who writes just deriving to JSON from JSON automatically as one thing, and I would love there was one single class, but yeah, I don't know. Cool, but okay, we have this encode and decode, but if you just write decode here, you will find a problem. And this problem is going to be that DHC will tell you, oh, I don't know what type you meant here. I mean, I should decode to which type. I cannot figure out what is the type you want me to use to decode this thing, because there is nothing in the rest of the code. So there is nothing that the inference engine could use to figure out that this is actually word 64 and not int 32 or unsigned beats 48. I don't know. But there is the good news is that in the current version of GHC, you can actually help the compiler by using this type application. So you can say decode as a word 64. So you are saying explicitly, oh, this should use word 64. And then, well, the compiler is happy because there is no longer an ambiguous type. It's actually knows it's word 64. And if you see, for example, here, that is enough information so that when you encode it back, you don't have to say word 64 again, because now you have given information about the decode being word 64, and then you create a random number, which is also a word 64, so it knows that when it has to encode it, it's working on a word 64 thing. So that's also something nice from using Haskell. You can give a few information, and then the compiler takes care of moving it around. Question? Yes? Oh, yeah, the question is what happens if the code fails? If the code fails, so actually decode returns an either, so you can get right or left. In good code, you should actually handle this case, although, I mean, if you have 8 bytes, in theory, you can always decode those at a word 64. So, I mean, I mostly did it because otherwise the code doesn't fit on the screen. But if you are decoding like more complex data, it might happen that there is something wrong. Like the typical case being you want to decode this as a string, and then you have ill form UTF-8 or UTF-16 or whatever a string, then it would return a left. But here, I mean, we are pretty sure if we have 8 bytes, we can turn them into a word 64. So I just went into the happy path and say, it will be right. If it happens, I still don't know how, but if it happens, you will get an exception, like a pattern match error. That's what will happen at runtime. Nice, so now it's your turn. I mean, I gave you the server. It's your time to write the client. And this is the type signature for the client part. So this is this. So the serve was for the server, and then you use connect for the clients to connect to the server. So I won't say anything else. The idea is that the same way that we look at the other signature, you look at this signature. The code is there. You can download it. So you only need, like the server is written for you, and you only need to fill in the blanks, the underscore. And by the way, if you have downloaded it 2 days ago, there is a new version because I changed some parts of it. And also before you start working on this, I know that some people, everybody will sort of ask me, okay, but how do I test this? So the easiest thing is that you open 2 terminals, one for the server, so you open GHCI or a REPL using Cabal REPL. Then you import dice roll, which is the module which has this, and then you run dice server, and then it starts. And as I said, it never finishes, so you need to do Control-C to stop it. And in other terminals, you open the client and then you make client requests. So hopefully, if everything works, you can make those work. You can actually see them in how it will work. There is a dice roll solution thing. So if you import dice roll solution, you are sure that the client works. Good. So I was told the other day that there was very little time, so that's why I've cut information for today. So let's work on this for, I don't know, 10, 15 minutes, and let's see how it goes. So these engineers over there are already, getting a bit nervous because what happens if the server goes down? What will the client do? An exception. And I don't know, but when I learned Haskell and somebody told me you get an exception, I was like, no way. Like, do we have also exceptions in Haskell? That was my first reaction. But yeah, there are actually, these things happen, right? The server is down, or in this case, you forget to start the server, and there is nothing to connect to. And what should we get back? So the designers, I would say, of the base library thought that, okay, we could go the route of, that's how I think that they work. So we could go the route of every IO thing returning like an either, because it could always return an error. But this is incredibly cumbersome because potentially almost every IO action can throw an error. I'm pretty sure even generating a random number can throw an error in very weird situation in which your system is misconfigured. So if you go that route, your code becomes unbearable to write. And actually, after writing this for years, I think that this exception mechanism is actually quite nice in dealing with these kind of I/O problems. And regardless of that, if we want to write good Haskell code, we need to deal with exceptions because they will arise. So just a brief introduction to exceptions. The Haskell I/O runtime uses exceptions for essentially input-output problems. They are somehow overloaded to some built-in features. So when you have a pattern match failure, for example, this will actually throw a pattern match error exception, which you can catch, and things like this. So maybe why you do this, it's not so clear. And even like undefined and error are actually implementing as throwing an exception. So if you open your terminal and write undefined, enter, then you will see exception, something, user error, something like this. So, apart from the feedback that I should do more, this exercises somebody told me, it's good that you tell us what not to use. So, my personal thing always the exception is that there is the control.exception from base, but I think you are better off if you use, as a beginner, the safe exceptions package or the unlift IO. So if you use unlift IO, which is a good, nice package for no one to go into that, they have their own kind of exception thing. And this has to do with the fact that actually exceptions in Haskell are more complicated because there are synchronous exception and like non-synchronous exceptions. And this is not hard to track. So somebody made a nice wrapper of like the good solution for 90% of the cases in safe exception. So I would highly recommend to use that if you are beginning to look at this. But regardless of that, all three provide exactly the same API, so it doesn't really matter. This is just like a small point that I think this means you won't get beaten by weird exceptions sometimes. So again, it's Haskell. We can do everything with functions. So catching, it's just a function, a regular function, which says, okay, I want to do something. That's the first M of A. And then I give a callback, which is going to be the handler of what happens when there is an exception. In that case, you get the exception E and keep going to produce M of A. So you run some action using the exception as input. That is as I said, the handler for the function. You can think of it even as a callback, right? It's the callback which happens when the wrong path is executed. And all of this is what it's done. Or you can also, if you want to kind of purify the problem or turn it into a data type, you can use try, which uses catch under the hood to essentially say, if the thing you did went in the happy path, I return right. If it goes into the bad path and throws an exception, I give the exception as a left case of an either. Just whatever you prefer for each problem, of course. So how most people use this is in this way. They write what they want to do, like connect and so on. That's more or less how like the dice client would look. And then they use catch infix. They use this backtick symbol, which allow you to put the name of the function in between the arguments of the function. So it's like when you write 1 plus 2, that you put the plus in the middle. So you can do this in Haskell for everything by using the backticks. I think that's how they are called. And then you have to specify the type of exceptions you want to catch. And to do this, you put it as part of the, usually, I mean, again, this is how most people use this. You use a scope type variable, which allows you to say that your E type there, your E variable there, must be of type IO exception. And the runtime system is clever enough to say, oh, if this is a function from type IO exception to whatever, this is the handler for the IO exceptions. So that's how, I can tell you how it works. Most of the time, this is the kind of thing which you just get in your head and you just write this. You know you have to catch exception, you write catch between back quotes, and then you write the handler. But something you might be wondering too is why I need to do IO exception. That's because there is actually a hierarchy of exceptions. So there's some kind of hierarchical structure on exceptions in Haskell. So there is like the top level called some exception, and then there is like different exception types, and they could branch, but most of the time they are in one level. So, question or comment? Oh, that's the name, right? Yeah, that's rude. So the name is scope type variables, and that's what you use to be able to write E : IO exception, but there is not a type variable. Yeah, I've never thought about that. That's right. It's weird. Yes. Write a GHC proposal. Oh, too bad. Now you have my. I'm no longer in the committee. You have my support. To write, I don't know what was the name you wanted to.
There's an exception called cannot signature, which you expect enables a cannot signature, and it actually became a synonym for scope type variables and then duplicated. So scope type variables is currently a bag of multiple things, including enabling this feature. And this is
Good.
scope type variable, yeah. But we are in the process of fixing it. So this wasn't an actual question.
Good. Just for the record, so they're gonna fix the scope type variables with a better name, which describes this kind of usages better. I think that's the summary. Okay, all right. Yeah, the exception hierarchy. So I said there is a hierarchy. So if you want to catch all the exceptions, and again, there is like a difficulty because there are like these asynchronous exceptions and things like that. But if you want to call all exceptions, you can use a handler for some exception, even though the best practices tend to be that if you want to swallow all the exceptions, you just use catch any or try any. But that's where the sum exception will come, and this sum exception is essentially, any exception. And you can use some kind of reflection facilities in base to figure out what is the type of this and things like this. So that kind of thing also exists in the base library, but it's all type safe. Cool. And the last thing about exception is that exceptions and laziness will make you dizzy. That's a normal feeling. And that's okay, but the thing is that makes resource management even more challenging than usual. And with this resource management, I mean, I need to talk to a database, and for this I need to initialize a connection to the database, and when I'm done with this, I want somehow this to be released, but actually I want to have a pool of connections, so there are 10 connections which are active or inactive. All this resource management gets even harder because of, usually you have to do something special because of exceptions. That's why you have try finalies in Java and C# and all of that. But here it becomes even harder because of laziness. means that you need to be more careful when things execute and when exceptions are raised. So just to give a few pointers, there are a couple of nice packages, resource-t and manage, which helps you with resource management. And there is a package called resource pool, which essentially can build on any of option A or B to have like a pool of resources. So that's for you to know, like if you go to the point where your server actually talks to a database, this might be the way in which you handle all the resources in your application. Nice. So that's enough for exceptions. We've dealt enough with this. Any questions? Yes. Mm-hmm. Yeah, so the question is like pattern matching exception will happen at any time and so on. So I think that there are like two answers to this. So one is like, if you look from it, like I think from an elegance point of view, it seems weird. But it's very useful, for example, to have a big throw, like a big catch any at the top level of your application, because if something happens, if something unexpected happens, at least it allows you to record it into, some login service or whatever, and look at what happened. And the information is there because it's a pattern match error. You can look at the call stack and figure out where this came from. So I think from an engineering point of view, there is a reason to do this as an exception, because it allows you to, and maybe only at the edge of your program, to be able to say, oh, wait, this is coming from here. We want to treat as any other problematic thing. But yeah. Question? Oh.
So we haven't talked about async exceptions, right? But do you think that except-t should be generally avoided because you have async exceptions? So catch error will handle async exceptions also, right? How do you choose when to use except-t, when to use exceptions?
Okay, so the question.
Synchronous exceptions to except-t, or is that an anti-pattern?
So the question is, when do you use except-t and how the async exception come into this thing? So the first of all is, like 99.9% of my time, I don't think about async exception because it made me even more easier. So I really don't think about them. I don't throw exceptions through different threads. I know this is used for some things, but I usually use libraries which has been developed around this pattern. So I never control async exceptions myself. That might be that's what I do. I don't know. And here I can only say about what I've seen in where I've worked. It's not. I don't know if there's how I like. But the other question about exception and except-t, how I like to think about this is that there are two kinds of things when you have a program. You have let's say your error in the sense there are actually three things in my head. So it's you have errors coming from validation. That's one kind of thing. And then I use usually a validation data type or something like this, or a parser. There is errors coming from your domain. So things which are literally things that may happen, but it's not a file is not there. It's literally that there is an invariant in your function which needed to be satisfied and it's not. So it's something which is, as I say, part of the domain you're specifying. Sometimes things go wrong. I like to use either or except-t for that. If it's in a transformer thing, I will use except-t, otherwise either or maybe. And then there are the other kind of errors, which is errors which come from I/O, as I said, a database connection has dropped and all of that. And in that case, they already throw exceptions. So that's maybe another thing. I almost never throw exceptions myself. I just let other people throw exceptions and then I catch them. So that's how I think of this. I think of these three things. And I think that except-t shines in when you have, as I said, you are doing something and you build your own transformer of the things you can do, and you have all these nice monad blah, blah, blah classes, and then except T allows you to have, or monad catch, to have something about errors in the thing you are describing, but not like the database errors. I don't know if that answers more or less the question, but that's how I think about it.
It does answer partially the question, but I'm just very worried about the fact that when I call a method, will I know whether it can throw error exceptions or not? And it seems like not doing it in the type system is just breaking the correction binary.
Okay, so that's
Always start throwing
okay. Yeah. So maybe the comment you're saying is that it seems weird that these exceptions are not in the type system, and maybe it should go into accept and so on.
This is an argument for except T, right?
Yeah, and all I can tell you is that I've grown sort of. Now I find that this design is actually really nice, because if you use except T everywhere, you are forced to, at each point, so at each instruction, let's say, you now have a let's pattern match, what to do in error case, what to do in other things. And for most cases in I/O, usually what you want to do is, I want to read this thing and connect to this database. I think if any of those steps fails, then I want to fail. But even more, maybe I want to have my failure logic, which in the case of this kind of side effectful thing, it's usually more complicated because you want to log it somewhere, or put it in one of these login services. This logic is usually complicated enough that you want to put it, let's say, at the top level. So you want to do all these things, and then if something fails because of these exceptions, you want to use this login service. And if you use except T, again, you have at each point to deal with this. You can use maybe a monad transformers and not look and not see this, but at the end of the day, you are doing it every time. And I think that's just a lot of boilerplate. I mean, you can see that, for example, the Rust people came with this question mark thing, which essentially says, if this thing has failed, then stop at this point and return nothing. And I think that pattern comes from the fact that like from a type perspective, it's so nice, but from a practical perspective, it's just so terrible. Like, imagine this code. So imagine this code where is it? Yeah. Where at every step, at every receive, at every send, I actually have to pattern match on an either and see whether it's left or right and figure out what is going on. And the only thing I will do, if there is a problem, is I will just return the same problem. So I don't know. All I can say is I've grown happy with this design. I think it is a good design, like a good space in design point. But yeah.
That begs the question whether Rust is doing it wrong, because I see a very direct analog between do notation on except T and question mark in Rust.
It's not exactly the same, because in Rust, so it's like you add at any point with this question mark, you are a pattern match, and then you do it there. So it's not like a whole monadic thing you need to cut. It's very localized. So somebody wrote a proposal called early do, which does exactly this for Haskell. So you can have a look. But maybe we should, we can keep discussing. But yeah, just for the sake of time. Good, we're good. Yes. So let's go to the next point of this. So we've been talking about I/O and exception, and the next thing I said, I'm going to talk about the serialization a bit more in depth. So, right. So imagine that now your program, your server doesn't have like just one thing that can do, like, you get a number and give back a number. It actually has different commands, right? It has different requests you can do. So how can you model this in Haskell? Well, you can just model it as a data type. So now our weird server is going to be able to roll a dice and also give you the next number of a given number. That's just because I'm lazy and I couldn't find another example, right? And my response is still going to be a number, because if you throw a dice, you give back the number. If you increment the number, you also get a number. And yeah, we don't care about overflows. I know about that. the point here is that I can express my commands and also my responses, if we have different ones, as a data type. And then, of course, we have this data type, and we need to write, we have to be able to serialize this and deserialize this and write boring code which, gets the first byte of the request, maybe, and look, if it's a 0, it is a dice roll, so it looks at the next 8 bytes. It's so boring. It's so boring that people just found a way not to do it at all in Haskell, usually what it's called automatic deriving, which is my favorite GHC feature of all times. That it allows you, it essentially, when you write the derive EQ and the derive show, and you don't have to write the quality thing because it's boring, or the show because it's boring. Well, in GHC, this is actually given in the hands of the library authors. So the person who wrote ASON used this to do it in such a way that you can also say derive to JSON and derive from JSON, and then the code is automatically written for you. You just, it gets the name of the fields and so on, and it just does the thing. Or like in this case, for the serialized instance that we need to use because we are using binary serialization. So it looks a bit like this. You need to, so you just need to add this deriving generic serialize, and it builds on a bunch of different things, but essentially in GHC, there are some type classes which are built in. So when you use derive, EQ, or show, there is actual code in the compiler which writes the code. But other than that, there is this generic mechanism to derive things. So in order to be able to derive serialize, you also need to add this deriving generic, and this is sort of creating a type level representation of how your type looks like, and then the next deriving serialize can use the representation from generic to write the code for you. Again, that's a lot of boilerplate. All I know is I write this line, this derive generic, derive any class, and then I need to remember to derive generic, and I can add here serialize from JSON to JSON, whatever that since I've learned about this, I literally written 0 lines, or maybe some of them, but very few lines of serialization code, because this takes care of it from you. So if we want to update our server size, we just do the thing and say, instead of decoding as a word 64 as before, now we have different commands, so I'm going to decode as a request, and this is this data type. And again, I've written the data type. I haven't written the deserializer. This has been written for us. And then the rest is regular Haskell code in which you then pattern match on the request. If it's a dice roll, you do the thing. If it's increment, you do your thing. So the rest then goes into normal Haskell code. And by the way, because we are pattern matching, the compiler is clever enough to infer the type, so we can just use the code there. We don't need to have the add request, because it knows that because we are pattern matching and it has a dice roll or increment, it must be of our request data type. And before I get the question, because I will get the question, then you will tell me, but if you do to JSON, maybe you want to use a different naming convention, because in Haskell you prepend the name of the type to the name of the field. Yes, there is something called deriving via, which is the best thing invented after bread, which allows you to do this boilerplate thingy, but introduce a bit of information, like, derive this, but by the way, while deriving the JSON, please put the field names all in capitals, or whatever you can imagine. So this is taken care of. It's more, it's called deriving via. It's a cool feature so that you know. Good, so, okay. Give you another 10 minutes for the second and last task. The rest is going to just be me talking, which is, take the code you have there. It's called dice roll increment, I think. So that's the whole server and client. And try to add a new command to say hi to people. And you can make it as flexible as you want. So it could be just a thing which says hi and returns hi back or something like this. Or you can make it something that can say hi to the, I don't know, how many languages are spoken in Switzerland? Like when I go to the train, everything is written in like 5,000 languages. So four, that's more than enough, yes. So that, like a Swiss greeting services, which is able to do this in, what is the fourth? You will tell me what is the fourth. I can, okay. Just take your time, 10 minutes or so, and yeah. And then we will talk about what happens if now we want more than one client, several clients working on the same dice rolling game. Hello again. Yes, so I think I'll take 10 more minutes. If you don't mind, feel free to go because you are hungry and things like this, and the lunch is already there. But I want to talk about the last part of it, what was the synchronization thing, and it's going to be, I won't go into so many details, but we want to now create this program. I want to call it Cloudy Rolly because it's, rolling dice in the cloud, and the idea is that there is the server, and then two players connect, and once they connect, they both say, I want to roll a dice, and then the server sends the winner. So I will show you how to do the first part, and it is that you do at home, other day, maybe next ZuriHac, the second part. But the thing is that from the serve, we get that each player runs in a different thread. So the serve automatically is spawning a thread. It's not really a thread. It's a lightweight thread handled by the runtime and so on. So it's super fast and whatever, but it's important for us that these are concurrent things of execution. So the question is, if everything is a thread, how do we weave those into a single thing? How do we communicate across boundaries? And then I will have my second no of the day. Base has control.concurrent, but that's a bit of, it's kind of a list of low-level primitives to build synchronization across threads. What you should be using is STM, that's software transactional memory, which, as I said, is the best thing I found for concurrency. And the idea is that you are going to do as if your variable in memory was like a small database. Everything that happens there happens in transactions, and transactions are atomic and isolated, which means that one cannot read the dirty state of the other transaction. And for me, the best example, what got me into this was, I have here a bit of code, and I will tell you what happens. So this new tvar IO is creating a tvar, a transactional variable, as I said, like a piece of memory, which is like a small database, and it's holding number 0. And then I'm gonna spawn threads. So async comes from a library called async, which is just an easy way to spawn threads. So again, you give it a callback of what you wanna do. That's what I wanna do. And I wanna do it 3 times. So I want to do the same thing in 3 threads. So I call replicate M, which allows you to repeat an action n times. So 3 times, I'm spawning a new thread, and in each of them, I'm going to run a transaction. And this is atomically is what tells you what is a transaction boundary. I use cool Unicode thingies. That's actually ASCII thingies to do this. So every transaction is just going to be read the variable and put back n plus 1. So if you are somebody doing concurrent programming, you will be screaming about this because you will be thinking, oh my God, it's going to be the case that one reads a 1, and then the other reads a 1 before the other puts the 2, and then instead of a 3, I will get back who knows what. Maybe a 1 or 2 or 3. We don't know. It's impossible. But if you use STM, your end value is guaranteed to be 3. Because this creates a transaction boundary, which means that for each of the threads, this thing runs atomically and isolated from the rest. So it cannot run in a dirty state of another thing. So 1 will see 0, 1. Other thread will see 1 and turn into 2, and the other will see 2 and turn into 3. And all I'm saying it might seem like overly simple, but the fact that this works allows you to, think of synchronization across threads in a completely different way, because now you don't have to care about like deadlocks or racing condition. They are just, you say this thing is going to happen in one go because it's a transaction. It happens in one go. And that's kind of the point of software transactional memory. Apart from, and the primitives are kind of easy. So you have like this atomically runs a transaction. So it's like, it delineates the boundary. And then within a transaction boundary, you have things which read your variables or write to the variables and things like this. And that's, if you only care about tvars, which are like just one piece of data, this is literally like all the API. You create a new one, and then you atomically can perform reads and writes, and they are in a transaction. So what we are going to do, and it's to think of this server as kind of a state machine, right? So when a user connects, they can send you new game if they want to be like the first thing, and then we send back like a game code, like a, let's say 4 string character, and then the other player sends join game with this 4 character code, and then we want to put them into the same thing. And because this is across threads, we need to somehow keep this mutable state, this shared state in a tvar. And there are problems, right? If they send the wrong code, we want to give back a game not found and close and things like that. So what we are going to do is to keep a dictionary of, when the keys are the game code. So when the first one creates new game, it puts a new key in the database, so to say, and then the values are the socket. So when we have 2 values in the socket, that means we know which are the 2 users. So that means that if you remember back this Go pattern I mentioned that sometimes you need to do some initialization. In this case, the initialization is going to be creating the state. So we need to create the mutable variable, which is, we use this new tvar, and then we need to give the type, which is the type of state, because in this case it cannot infer it, and then it's an empty map. So that's an empty hash map coming from containers library. And then my worker, the thing which goes in a loop, is essentially going to be these 4 definitions. So I start, then I want to pattern match. If I get a new name command, I will execute new game. If I get a join name command, I execute join game. And at the end of both, I will call play. And that's the part you need to implement. In this case, I just show play to the screen. Yes, so it looks a bit like this. Hopefully, if you have questions, I'll try to go into this a bit faster to focus on the STM part. So here I'm just using JSON instead of serialization. That's because this thing has different amount of arguments. Otherwise, it's hard to know how many bytes are and so on. So I don't want to think I just use JSON. So what I do is when I start, I receive JSON, and then I can have 2 different commands. Depending on this, I execute the other function. So hopefully this is straightforward. And then let's go to the meat. In the new game, what I do is I get a random code. I wrote somewhere a thing to give me a 4-letter thing. And then atomically, so in one go, I go and modify the state by inserting the code and my socket. So that's my boundary in this case is small, and instead of, the idea is I read and I put back the same thing, but now with an extra key. But of course, there is a modified tvar which does this for you, reads and then writes back something. And then I send back the game code to the first, so that the first user says, oh, this is the code I've given to you, give it to the second user, and then you can both join the game. And then what I do is I will wait for the other message. And I will wait for the other message by reading the state and looking up the game code, my game code, and then waiting until the length is greater than 1. And that's the second thing that STM gives you. There is something called check, which aborts the transaction, so doesn't do, in this case, there is nothing being done, no modification, but checks abort the transaction if the condition fails. Or unless the condition fails. It checks if the condition is false. But the cool thing is that the runtime system knows about STM and will only retry it when some of the t-bars change. So this is not a tight loop checking all the time. This is actually just waiting until somebody changes the variable, so change the map, and then it goes, executes the transaction again, and will check again. If now we have somebody for the new code, we keep going. So that's the trick. And the thing is that this, again, maybe simple, stupid thing means that tvar can work not only as a shared mutable state, but also as a synchronization mechanism, right? You can use this to implement a semaphore or a lock or something which requires synchronization by just having a check and knowing that the runtime system will only re-execute your transaction when something changes. Like if you have a semaphore when maybe your amount of allowed people is now greater than 0. So you don't have to care about this. Yes, and then we have the join game, which again, it's big, but essentially you have this big transaction in which, so that's the second person, right, joins the game with a code. So what we do is we look if the code is there. If the code is there, then we add ourselves. That's this modify part, so we add ourselves, and that's because we added ourselves. The other thread, the other part will know, oh, something has changed, let me rewrite the transaction, and then I will have 2 people there, so I know I can start the game because I have the 2 sockets to communicate with each other. And yeah, so then, yeah, and then we have some management here because actually a transaction may include some pure computation. So you don't only have to read and write. You can read and say, if it's greater than 1, I write, and so on. So in this case, we are using this to check, okay, if the code is not there. So this map lookup comes from this container library and tries to look up in my dictionary. If it's not there, returns a nothing. And in that case, if you see the whole code, this returns false. And then the false means it's not found, so we return a game not found. So it's a bit kind of logic going on there. But the point I wanted to make here is that your transaction may not be only read and write. It could be read a bit and execute a bit of computation and then go on. What you cannot do within a transaction is other side effects. That's the only thing which is disallowed. So it's not I/O. It actually runs in its own STM monads to do this. Good. So there is no more time for practice. I knew that. But that's, I said I changed the slides. I changed the slides. I add that. Now, but if you want to, think about it a bit more, you can finish the implementation of the server by changing the state instead of just being like the people there to actually represent the state. So something from game code to game state, which says in which state of the game you are. And again, try to use this tvar asynchronization mechanism because, as I said, what the server should do is wait until both people have sent the roll dice command, and then when both are in, then the random thing is done, and then the winner is sent. So there is some synchronization being done there. So, try to use that too. But the most important thing is that you can do all of this with a single play implementation, so you don't need to distinguish whether you are the first player who joined or the second one. You can do this in just one go. And of course, you can write the implementation of the client. That won't involve any STM because that's just normal I/O. Cool. The last thing, and that's just because I often get this question when I talk about STM. Yeah, but won't this, I said that you retry transaction. Doesn't mean that if I have too many users, and I am re-executing transactions all the time, this would have like, a lot of contention, like overloading the STM mechanism. And the answer is yes, because every join game, so to say, will wake up every new game waiting to check if the code is now there, so if they join that game. So you can imagine you have like thousands or millions of games. This could be bad. Because we actually, for each thread, we only care about one code, whether the code we are waiting for has now 2 sockets or not. Good news is that people have been developing more fine-grained data structures. So actually, in this case, you wouldn't use a tvar. You will use a tmap, which is a map which knows about transactional things. So for example, it's more fine-grained that if you have only looked in your transaction and this key, it will only retry if this particular key has been changed and not in other cases. And there are so many. There are STM containers, which has maps and set. STM itself includes some bounded queues and then chance bounded queues, because another thing you can do with this is create like worker queues, right? So you can like work goes in one place and then there is a bunch of people listening to it. So that's again something I haven't gone into, but like you can sometimes duplicate this thing and several people be waiting on the same stuff to create like a, like a worker queue where somebody can take it, and then if I take it, then the rest don't see it, and so on. So this gives all the time. Like with tvars, people have been building this abstraction, and this is so nice. Good. Questions about this before the summary? I will just. I promise I'll finish soon. Question about STM. I see excitement faces. That's all I wanted. Great. So the idea today was to, tell a bit about how you do I/O in more than, if you read the programming in Haskell book, that's great. There is some I/O, but that's essentially like I read a file and then I write a file and, what if the file is not there? Book doesn't say. So, I've introduced a bit about the exception for I/O errors, talk about a bit how you can do high-level networking with Network Simple, but the goal there was that there are so many of these libraries which take care of doing things for you, like listening, and then they often use this callback mechanism. You often give functions to what should be done, so I think it's a useful pattern if you are doing Haskell. And then automatic deriving is like the best feature ever written in a compiler, and then STM is the best library ever written as part of the runtime system, actually. I haven't talked about other things which I think are interesting, so I sort of hinted that there is an async library to create your own threads, which literally works by having an async function, and that's all you need from the library. And then, I also sort of hinted that there is a Monads I/O, but if you are using like Monad transformers, sometimes you don't really talk to I/O directly that we are doing. You use a Monad stack which has I/O, and then you need to learn how to use Monad I/O and either Monad and Lift I/O or Monad-based control or some of those other abstractions. So I haven't talked about that. I'm assuming that we do everything in I/O, but you have seen that, for example, the Network Simple library use Monad I/O in the type signature. So it's present everywhere in the Haskell ecosystem. So that's all. I've written another book. So if you want to read more about libraries, you can give money to Limpath, and then some of them will eventually come to me, which is great. Other than that, it's been a pleasure. Enjoy, if you can, the rest of ZuriHac. I guess today will be an inside thing. And thanks. I'm here until lunch if you want to talk a bit more, and then I'll be going to Zurich to travel back home. So that's all.
Thank you very much, Alejandro.
Welcome.
Cool. So that was this morning's session. What time is it? It's 11:45. Lunch is already available, so if you're hungry, you can go down and have lunch. I will have another small beginner session right now. So if you are in the beginners group and if you have some questions, want to meet and talk and things like that, I'll meet you in our normal room. We'll try to keep it short, maybe 10, 15 minutes or so, depending on what you want me to do. Cool. Then I'll see you there. And the next fixed point for meeting for us today will be the project presentations at 3:30. So see you then. Thanks.